So topic 1.13 called function model selection and assumption articulation, which is a lot of words to say we're working on making sure we can look at real world data and real world scenarios and decide what type of function that we studied so far in class best represents that data. Okay, we're going to focus mainly today on linear, quadratic, and polynomial models, so we'll leave rational functions for a second and focus mainly on these types when we look at data. The thing about data is it's not always perfect. So when we're looking at real world things, it's not going to be a perfect rate of change for a linear model, but it's going to have a roughly constant rate of change. If this was the data I have, do you see that that data is roughly linear? If I were to look at every single distinct point, it may not give me a perfect constant rate of change, but I will have a roughly constant rate of change in my data. There is a constant or roughly constant first difference in output values over equal length input value intervals. The output values are always just increasing or decreasing, and contextual situations that demonstrate roughly constant rates of change can be these linear functions. So again, we talked about at the beginning of this class constant rate of change meaning linear, and that's great when it's a cute little math problem, but when it's real world data, it's not always perfect, but if it's roughly linear, then we're going to choose a linear model to best represent this data. Same thing goes for quadratic. Let's say that I have data that does something like this. Is that a perfect parabola? Is it roughly a parabola? It's real rough. I didn't draw a very good one. Let me make it look a little nicer. Like, what if it looks like that? Okay, that's pretty roughly quadratic. So when we're looking at quadratic data, we would see that the data has roughly constant change in the rate of change. Same vibe as before, but it's not going to be perfect. It's going to be a rough constant change in the rate of change, okay? Or a rough constant second difference when we have equal length input value intervals. The output values will indicate rough symmetry, meaning like if you have a certain height on this side of the axis of symmetry, then you'll have the same height on the other side of the axis of symmetry. And it will have a unique minimum or maximum value in the data. So if you see it go up and then start to go down and never go back up again, it's probably quadratic. Interesting here is contextual situations that involve area. So the geometrical property of area is a length times a width. Length times width is a two-dimensional shape, so that's x squared, which means we would use a quadratic model for that data. Bless you. Now, if we go to higher degree polynomial models, we may have something like this, which only some of us remembered the name of it at the door. What was that one called? Starts with a C. Cubic. So it's a degree 3 polynomial would be cubic. And this is a bonus. I didn't ask this one at the door, but if we had roughly data that looked like this, what would that one be called? Quartic. I heard it. Very good. You don't have to know those names off the top of your head. You do need to recognize them if you were to read them. But if we're looking at polynomial with nth degree differences, then it has a roughly constant nth difference, whatever that degree is, over equal length input value intervals. In both of these types of functions, you will have multiple maximums and minimums. So if you notice the data is increasing, then decreasing, then increasing again, that's probably going to be a cubic or higher degree polynomial. For contextual or geometric situations here, we're talking about volume when it comes for cubic functions. Since volume is a length times a width times a height for a three-dimensional shape, that's a three-dimensional shape, so it's x cubed, that's going to be a cubic degree or a third degree polynomial called cubic. Okay, so as a quick review, in a nice neat conversation right here, it says which function type best models the data in the tables below, give a reason for your conclusion. There's no context to these problems, and this data looks really nice. So we can just do what we did at the beginning of Unit 1 and check to make sure that we have equal length input value intervals. Do these change by the same number, the x's? So we have equal length input value intervals. All we have to do instead of doing a whole average rate of change is see how these numbers change. How do you go from 4 to 7? How about from 7 to 10? 10 to 13? And 13 to 16. What do you notice there? It It changes at a constant rate. So we know that this data is best going to be modeled by a linear function because, again, there is a constant rate of change. Okay, so again, the questions today are going to be which type of function best models the data. And since we see that the first difference is, this is degree 1 that's linear, or if we notice that there is a constant rate of change, the rate of change does not change, meaning this is a linear function. Does this sound familiar from the beginning of the year with me? Okay, good, it should. Let's do one more just to practice. Does this one have equal length input value intervals? Yeah, so we can do the little, I don't want to use the word shortcut, so air quotes shortcut, where we don't have to do the entire average rate of change. We can just see how these numbers change in the outputs since we know the inputs change equally. How do you go from 0 to -1? Subtract 1. How about from -1 to 0? Add 1. Automatically, we can kind of make a conclusion here. Is this going to be linear? Definitely not. Okay, let's keep going though. How do I go from 0 to 3? How about from 3 to 8? We know that those average rates of change, or the first differences, are not the same. So we keep trying the second differences or consecutive differences. How do I go from -1 to 1? And then 1 to 3? And then 3 to 5. Ah, this time, what do we notice? These numbers are all the same, so what conclusion can I draw? What type of data is this? Quadratic. Now the reason, you can give me multiple different types of reasons that this is quadratic. The one I'm going to write down has to do with the rates of changes because that one's the most uncomfortable, I think, for us. So we can say there is a constant change in the rate of change. And that would be going up by 2. The constant change in the rate of change. The rate of change changed by going up 2 each time. I know that's the word change like 80,000 times in one sentence, but that's how we describe it. Another way to describe this would be that the second differences are roughly constant or are exactly constant. So that's really great. But then we're going to take a turn on example 2 here. In example 2, do you see how this models like data looking data, not just numbers, right? This looks like we ran some sort of science experiment and we have all of this information. When we run our own science experiments, our data is not going to be nice, pretty, perfect, where we can do these mathematical questions like we just did in example 1. Because first of all, do my t values, my input values, change over equal length input value intervals? No, this one goes up by 0.4 and then 0.5 and then 0.3. So we're not using equal length input value intervals. So we would have to do the average rate of change for all of this data. Or, since it's a calculator day, we're going to do the following. I see some of us have already picked up our calculator. What is your brain wanting to do when it sees a table on this calculator? Nobody? Ooh, our instinct should tell us that we're going to go to stat and then over to edit. You're going to want to type in the entire data table to your calculator. And yes, that's a lot of numbers, so I'm going to pause for a second and let you type them in. You can't just type 2 or 3 because we're using real life data. We need every single data point possible to write the best regression line. So if it's been a minute since you did stat edit, L1 should be your input values. L2 should be your output values. So we're going to put all of the t values in L1 and all of the h of t values in L2. And we're wanting to see what type of data best models this situation that we have. So we want to see all of these data points on our screen. To do this, follow along with me. You're going to press y equals. And if anything's there, clear it out. You're going to go up to plot 1. You have just plotted data into L1 and L2, so you need to turn on plot 1. Typically when you open this, it's like this where these are not highlighted, but you want to go turn on plot 1, which is programmed to show you the input values in L1 and the output values in L2. Okay, if you were to do that and you go look at the graph and it's on the regular zoom, because you should have restarted your calculator when you picked it up, this is what it would look like. Do I see all of the data on my screen? No, so we need to zoom in a different way to see all of the data on our screen. Now I know I've typically said you have to press the window button because I need the window button to be used here. Okay, so when we get to a statistics plot, there is actually a helpful hint on your calculator. You actually are going to press the zoom button instead of window. And the zoom button has an option down here, option 9, that says zoom stat. You want to zoom to where your statistics are showing really well. So you're going to press option 9, and it's going to show you all of the data you typed into your table. If you follow those instructions, what does this data look like? Quadratic. So we know based on what the data looks like that it is roughly going to make a parabola, which means this data would be quadratic. So to write down some more tips for ourselves so that when we look back on our notes, we remember what we did. We did stat edit, type t into L2 and h of t into L1. We're going to go to y equals and turn on stat plot 1. I guess it says plot 1, but you get what I mean. Turn on stat plot 1. And then to see the data very well, we're going to let the calculator work hard for us. We're going to press zoom 9, which is called zoom stat. It's going to zoom to the best place for you to see your statistics that you've typed in, which is all of that data point. And then again, for this data, we saw that our data looked like this number-ish. And so we concluded that the best function type would be quadratic. This would be really hard to do by hand because this data is roughly quadratic. If I actually found the second differences, they're barely second differences that are constant. So it would be very confusing for us if we didn't have this piece of technology to make the correct conclusion about this data. Now, the first time we do anything on these calculators, it feels like, yeah, that's easy. And then if I tell you to do it again, everything jumps out of your brain. So right now, I want you to second plus 712 your calculator and try everything one more time, just to make sure you actually caught all of those steps. And now I'm not showing you, I can walk around and help if you missed anything. So second plus 712, start it all the way over. I want to see the same problem again. We did these first few problems from a table to decide what kind of function best models the situation. But what if we open this up and we have a word problem scenario that asks us to solve a problem where we have to choose the right type of function. Okay, this is a very complicated problem because we're going to have to choose a type of function, create a type of function, and add restrictions to the domain based on real life things. So the question here says, a cool deck is placed around a rectangular pool. By the way, that's not like an adjective like cool deck. It's a cool deck. It's like a cool deck, like your feet are cool when you walk on it, a cool deck. I had to Google that because I thought it was interesting that they left the word cool in this example. Anyways, not important. It is placed around a rectangular pool. The length of the pool is 3 times the width. The cool deck will be 2 feet wide along the length of the pool and 3 feet wide on either end. Write a quadratic polynomial model for the total area of the pool and the cool deck in terms of the width of the pool, WP. If the width of the pool can be no larger than 20 feet, what is a reasonable domain and range for this problem? We got a lot of things going on. Let's first understand what's going on. Here's the pool. Great, this pool has a length and it has a width. Acceptable? Then around this pool, there is a deck, a cool deck, surrounding the pool. This cool deck says that it extends 2 feet wide along the length of the pool and 3 feet wide on either end. So I can say that between here and here, this would be 2 feet, and between here and here, that would be 2 feet. Along the widths, we would be 3 feet and 3 feet. Yeah, it's not to scale. Okay, we get it. I'm not an artist. drawing artist. Okay, here's what we need to do. We're writing a quadratic polynomial. So they gave us a hint here, a quadratic polynomial to model the total area of the pool. Our job when we're finding area, just in general, is to multiply the length times the width. And if we apply that to our problem, we want the area in terms of length WP, which means I want my variable to be the width of the pool. Okay, which means that I need both of these things, the length and the width of this pool, to be in terms of WP. Easy peasy for the width of the pool, since that's literally the width of the pool, WP. We've got that right here. That's the width of the pool. But we go back to the question here to see how to write the length in terms of the width. This question says the length of the pool is 3 times the width. Okay, how do I write length of the pool is 3 times the width? 3 times WP would be the length of the pool. Yes, length of the pool. But the thing is, we're trying to find the area of the pool deck. So these are not the right dimensions to use, because this would only give me the dimensions of the pool itself. For the length of this pool, what do I have to add on either end of the length to have it be the length of the deck? 3 on each side, right? So in fact, the area with respect to the width of the pool of the pool deck would be 3 times the width of the pool plus 6. And the width of the pool, cool, fine, whatever, but how much longer is the width of the deck beyond the width of the pool? How much extra on this side? How much extra on this side? Which means in total, how much extra? 4. So we're going to take the width of the pool and add 4, and that would create the width of the pool deck. Since we want this to be a quadratic function, we do want to multiply all of this out, so we're going to practice foiling for a second. If you're looking up here and you're like, literally, why are there so many letters? I get it. This is area. This is standing for width of the pool. We had to specify that it's the width of the pool because we have the width of the pool deck and the width of the pool at the same time. So we use a subscript to talk about which width we're talking about. If we go ahead and FOIL all of this, we would do 3 WPs times WP, which is 3 W of the pool squared, width of the pool squared. And then we have 3 WP times 4, which is 12 times the width of the pool. Then we would have 6 times WP, which is 6 times the width of the pool. Then we have 6 times 4, which is 24. When we're doing FOIL, if you've done it correctly, there is usually stuff you can combine together in the center, which means that our area of the pool deck with respect to the width of the pool is 3 times the width of the pool squared plus 18 times the width of the pool plus 24. There's our model that we created to represent this information, which, by the way, is measured in square feet. Units are important, right, physics friends? But our question goes on, because when we create these mathematical scenarios, we have to make sure it makes sense in real life. We have to give it a correct domain and range. So we are going to adjust this question so that the domain and range makes sense. Here's the domain of the function. We know the domain is the input values. So what's the smallest input value I could plug in here? Remember, our input is representing the width of the pool. What's the smallest width of the pool I could use in real life? Yes, but I'm going to make it 0, just bigger than 0, not equal to 0, because you could have a width of the pool being 0.1. You probably wouldn't, but you could. You just can't have the width of the pool being 0 or any negative number, because you can't measure things that are negative in length. And then the problem has a restriction for me. What's the largest the width of the pool can be? Read the last sentence. 20. So the largest it can be is 20. Notice I switched to using less than or equal to because it can be 20. Which means the domain for this function is from 0, it should be a parentheses, is from 0 to 20. Great, we found the domain. Now we need the range. If you remember the relationship between domains and ranges, domains are inputs and ranges are outputs, which means to find this problem, to find this answer, I need to figure out the area if the width would be 0, and I need to find out the area if the width would be 20, because those two outputs are going to be my range. So A of 20, what I've written down right here literally just says to plug 20 into my function. I mean, sorry, not 20, 0. To plug 0 into my function. If I plug 0 in here and in here, what's the output? 20 what? 24. If you plug in 0, the first two terms cancel because they're multiplied by 0, but the constant term stays. So the smallest the range will be is 24, or just larger than 24. Now what happens if you plug in 20? Ooh, good thing we have a calculator today. Can y'all plug in 20 to that function, please? What do you get when you plug that in? 1,584. I agree, 1,584. So my range, the smallest it will be is for the width of the pool. No, sorry, this is area. For the area of the pool would be just larger than 24, all the way up to 1,584. And if you're in physics, because I want to help my physics friends out, this is feet, this is square feet. Units are important. Because we have a width as our input, that's a feet. We have an area as our output, that's a square foot. So here's what we had to do on this problem. If we jump back a little bit, okay? We had to understand the scenario we were given, which was the lengths and widths of a pool. We had to understand that this was area since it's a two-dimensional shape. We had to use all of the pieces of how the graph relates, or how the equation relates to each other, how the width of the pool relates to the length, and how those relate to the pool deck. We wrote our whole equation, we got a nice looking area formula, and then we decided the domain and range. Some things to remember is that in real life, you can't measure things that are negative. So the smallest measurement you'll ever use is just bigger than 0. So we use 0 less than, not equal to. That was a lot. Can we do another one that's honestly slightly easier? Example 4 says, a fish tank in the shape of a rectangular prism, aka a box. Let W be the width of the fish tank. The height is twice the width, and the length is twice the height. Write a function to model the volume of the fish tank in terms of the width W. If the height can be no more than 24 inches, what is a reasonable domain and range for this problem? First of all, we're going to draw a box so we can understand what's happening in this scenario. So here's our rectangular prism. That was actually pretty good for me, not going to lie. When we are measuring the volume of this fish tank, which is what we are looking for, because it says volume right here, we know that that's a three-dimensional measurement. It is length times width times height. That's volume. So typically when we find volume, we would just say whatever the length is multiplied by the width multiplied by the height. The problem is we have to write this entire functions in terms of the width. So we need to get all of the letters to be W's. So we read the problem to see how to get this to be in terms of W. Volume in terms of W. Okay. I need something for the length here. What's the relationship between the length and one of the other variables we have here? Length is twice the height. So instead of L, I could write down 2H. Yes? And I'm just going to do one piece at a time here so we can see what's happening. Now I have two pieces that are in terms of height and one piece that is in terms of width, which is what I want. Let's get rid of the height. Is there a relationship between the height and the width? What is that relationship? So the height being twice the width, meaning everywhere there is an h, I can put 2 times the width. And then I have a width, and then I have 2 times the width. That's a weird looking W. If I combine all of that together to simplify, I don't have to FOIL anything here because there's no pluses or minuses. These are all monomials. I'd have 2 times 2W times W times 2W, which is what when you multiply all of that together? 8W cubed. There's our formula for the volume of this fish tank, and our units inches cubed, relating all of them in terms of the width of this fish tank. So we rewrite the formulas in regards to the one letter that we care about, which in this case is the width. But of course, because this is a real-world scenario, we need to understand the restrictions. How big can we make this fish tank? How small can we make the fish tank? These are things you actually think about for real-life problems. Let's do the domain here. If I deal with the domain, I need the smallest input value I can use. So again, what's the smallest or just under the smallest domain value I can use? 0, because I can't actually make it 0, but I can make that width real close to 0. What's the largest?
Sorry for the interruption. Teachers,
Yeah, straight up, where were we? Oh, we found that the smallest number we could plug in was just bigger than 0. What's the largest number for the domain I can plug in? 24, because it said the width can be no larger than 24 inches. So my domain is going to be from 0 to 24. Say again? Oh, it sure does. Thank you for catching that. So it says that the height can be no more than 24 inches. Here's what we're going to do then. We're going to change this from a W to an H. Thank you for falling for my trick. I totally meant to do that. But we want this. Why did I put a 2H? This is height. Oh my gosh. I'm losing it. But we want this in terms of W. Yes? What was the relationship between H's and W's? H is equal to what? 2W. So I could replace the H with a 2W. And that's great. But I don't care about my domain in regards to double the width. I care it in regards to the single width. So I'm going to divide everything in that current inequality by 2. 0 divided by 2 is 0. 2W divided by 2 is W. 24 divided by 2 is 12. That's much better. These are numbers I recognize now, which means my domain is actually from 0 to 12. Now, even though I almost just fell for this trick, why could we not just write from 0 to 24 for my domain and leave it like that? Yeah, that's not our inputs. Our input in this formula is W's. We need our domain to be about W's. That's our input values. But of course, now that we've done the domain, we can very easily do the range because we have a formula that gets me from my domain to my range. So I need to know the volume if we had a 0 for the width. And then I need to know the volume if we had 12 for the width. If we plug both of those numbers in, what's V of 0? 0, because there's no constant there. And then V of 12 is going to be a large number. Can somebody figure that one out for me? Who types the fastest is that question, you know what I'm saying? It's a big one, yeah. It should be 13,824. Is that what you got?
No.
Oh, dear. 8 times 12 to the third power. Make sure you put parentheses around the 12. Oh no, do I have the wrong number written down? Totally possible. No, I stand by my answer. Okay, listen. We all know what day I've already had. Yikes. Okay. Now, these problems, very hard. Yes, but this is the level we're going to try to get to. This is what actual mathematicians would be doing with data and analyses and going all the way here and understanding the restrictions of the functions they're creating or the data that they gather. This is the end goal. For my physics friends, let's add some units because I don't want you to think that we don't care. But this is feet. Nope, just kidding. We're measuring in inches. This is inches, and this is cubic inches. There you go, my physics friends. Okay, so what we've done so far. First page today, we talked about deciding what type of function best models data from data sets. We then looked at data sets or scenarios and created models for them and talked about restrictions on those domains. The last part of today is looking at what are called piecewise functions. These functions are really cool, but they're a little bit complicated. I like to call piecewise functions Frankenstein graphs. That's not an official name. That's a Miss Quigley name for them. But if we think of them like Frankenstein graphs, they're going to be multiple graphs put together in different ways. What's going to happen in a piecewise function is we will have different definitions for different intervals, meaning you'll have some value, some equation, f of x, that is in charge of the graph over a particular domain. And at some point, it's going to switch what's in control. So at some point, g of x is going to take over a different domain, which honestly, this is a straight up typo. This should be a less than sign. Okay. So it tells me that when my input values are less than a particular number, that blue graph is in charge. And then once the input values are bigger than a certain number, we switch to another one. So we're going to have a Frankenstein graph with multiple parts of a graph taking over at different intervals, at different domains. They're called piecewise defined functions. I like to call them Frankensteins. First things first, let's just make sure we understand how to read a piecewise function in the way that it's written. So for example, 5 here, we have two functions. We first have the quadratic x squared plus 1 that is going to be in charge of the function when you're plugging in numbers that are less than 0. We have another linear function, x minus 1, that's going to be in charge whenever x is greater than or equal to 0. So our job when it comes to piecewise functions is to understand what input variable value goes into which part. So this first question says to do f of negative 5. I'm wanting to plug in the number negative 5. Is negative 5 less than 0 or bigger than or equal to 0? Less than 0. So I'm going to take negative 5 and I'm going to plug it into that red function, x squared plus 1. Because, bless you, because I know that negative 5 is less than 0, so it goes in the red one. And then after that, it's just like an arithmetic question. Negative 5 squared is 25 plus 1. That means that this is 26. The end. So we're reading the domain restrictions to know where we're plugging in our number. The next problem wants me to evaluate f of 0. Would I plug 0 into the red or to the blue equation? Blue, because 0 is equal to 0, so we're going to want to plug it into the 0 minus 1 part. That's the blue, because 0 is greater than or equal to 0. Well, that's easy. 0 minus 1 is negative 1. I'm done. Now, what about f of 4? Am I plugging in 4 into the red or to the blue? Blue, because 4 is greater than or equal to 0. So again, I choose to plug it in to the blue part because that's the domain where the x value of 4 would exist. Yes? Yes. Does that make sense on how to read the way an equation is written for a piecewise function? It tells you which part is in control for what x value. If we look at example 6, it says write the piecewise function that best models the situations given. There are 3 parts to this function. Highlight along with me. We're going to have the first part, this flat line. Then it abruptly changes to this linear portion. And then it abruptly changes to a positive linear portion. We need to write the piecewise function that controls all of that information. Okay, if I were to only look at the red part, and this red, don't draw this part in because it might be annoying for you, but if this red line was extended all the way across the graph, what would be the equation for that line? Y equals 2, because it's a Hoy line. It's a horizontal line at 2. So my piecewise function is going to start with that information. It's going to start with the fact, so f of x equal to giant squiggly, that the top equation, my first equation, is just 2. But that graph, besides the fact that I colored in more, where does it start? Where does that little red part start? What x value? Where does it stop? -1. So we're going to say that 2 is in charge when x is between -3 and 1. Sorry, -1. Now you might have noticed something. What do you notice that I put on the first sign that I did not put on the second? The equal to. Now this is confusing because there's a closed dot there, yes? The problem is because I need this to be a function, I'm going to let the blue graph actually be in charge at that dot. Meaning, if I go to make the equation for the blue line, right? This is a linear equation. What's the slope of this linear equation? If it were to continue for forever. -1. What's its y-intercept? 1. So this blue graph is -1x plus 1. And since it hits right at the same part as the red function, I'm going to say it starts at -1 and give that one the less than or equal to sign. They both can't be equal at the same time, otherwise you don't have a function. So we're just going to assign one of them. We don't have enough information to decide which one it belongs to here, so we're just going to give it to the second one. Where does the blue graph stop? 2. So same thing, I'm just going to say less than 2 because of that closed dot. I'm going to assign to the green line so that the green line is can control. But if we look at that green line and pretend like it extends all the way through our graph, right? What's the slope of that line? +1. What's the y-intercept of that line? -3. So my equation for the green part is going to be +1x minus 3. The x values where that one's in control, where that part shows up, is from 2 all the way to 4. This time I gave both the less than or equal to's because I'm just assigning both closed dots to be a part of the green. We don't necessarily have enough information on this particular problem to know the difference between those. But if you see an open circle, you just put the less than sign, not the less than or equal to. But do you see how we have this complicated picture that is controlled by 3 different functions over 3 different domains? That's a piecewise function, or like I like to call it, a Frankenstein graph. Another way you may see piecewise functions is through a scenario here. This scenario says, starting at time t equal to 0 minutes, a copy machine makes copies at a constant rate of 80 pages per minute. 1 minute after the first copy machine begins making copies, the copier starts to hole punch the copies, so it slows down to 50 pages per minute. The copy machine continues to make copies at this new rate until t equal to 3 minutes. Let C represent the total number of copies made by the copy machine after t minutes, and write a piecewise function that models the function C. So do you notice that in this scenario, we have like 2 parts? We have the first minute, where it's only one copy machine going at 80 pages per minute. And then after 1 minute, the copier starts to hole punch the copies so it slows down to 50 pages per minute. Those are my 2 functions that are going to control the output of this copy machine over my 3-minute interval. So if we started to write this, we would say that the number of copies with regard to time would be controlled by the 2 scenarios. The first scenario is 80 pages per minute. How do you write an equation that says we're spitting out 80 pages per minute? Yes, but we're going to use t's, so it'll be 80t, t for time. Now, this is in control for only the first minute of making copies. So we're going to give it from 0 to 1 as the time where this part is in control. 80 pages per minute. But then our copy machine starts to hole punch it. So it slows down and now it's at 50 pages per minute. How do you write an equation that says it's spitting out 50 pages per minute? 50t. Now pause before you start writing more things because this is not finished. Remember, our copy machine is a continuous function, which means we need these two parts to meet up. After 1 minute, read 1 minute, how many pages have been spit out? 80. If I were to start right away at time equal to 1, my blue function would give me an output of 50. But what should the output be at that we just found? 80. So how many more pages do I have to add to it so that we start at 80 pages? 30. So my y-intercept for this graph would be 30 because we need them to switch off in a continuous way. So after 1 minute, these both would give me an output of 80. But then the second copy machine rate, which is 50 copies per minute, starting with an additional 50, continues to make copies until 3 minutes. So we're going to say at 1 minute, it switches over to this, and it ends at 3 minutes. So two things to think here. We got kind of the 80t, 50t easy. What we need to remember too is that since this is a scenario where the copier is like continuous, it just shifts its rate, we have to get these two to match at the point of switching. So at 1 minute, there's 80 pages out, and at 1 minute, there's still 80 pages out. You have to get them to match up. The last way you're going to see a piecewise function presented to you, so to recognize it, is potentially in a table. This table says explain why the data set below models a piecewise linear function. Now, first thing I see is since it's a table, I hope it's easy. Is this equal length input value intervals? Yeah, so this is an easy problem. All we have to do is figure out how these numbers are changing. How do you go from 10 to 5? How about 5 to 0? How about from 0 to negative 5? But then all of a sudden, I go from negative 5 to negative 3. How does that work? Don't overthink it. How do you go from negative 5 to negative 3? Plus 2. And then negative 3 to negative 1? And then from negative 1 to 1? Oh, snap. So weird things are happening, yes? If we stopped right away, we would see that we have initially a linear function because all of this is the same. But then, whoa, we have a separate linear function because it's a constant rate of change in two intervals. This is our key to noticing that this is probably a piecewise function that's going to have a red linear function with a slope of negative 5 and a blue linear function with a slope of positive 2. So why is the data set a piecewise? We would say something like this. We would say the rates of change are two different constants over two different intervals. We originally had a rate of change of negative 5, and then we switched to having a rate of change of positive 2. That's our indicator that not only do we have a linear function, but we have a piecewise linear that switches from being linear with a slope of negative 5 to linear with a slope of positive 2. That's going to be our break in our Frankenstein graph. So we're adding complications to all of the things we'd already known before.